So how are things going? So how was the topics we covered last week? It's still may feel like it's part of like the systems we'll look at later in this course, but hopefully it'll bring you up to speed for a whole bunch of stuff. Right? If nothing else, you'll probably use it when you go to Best Buy or something to buy stuff. Right? And part of the lecture today covers sort of the same kind of stuff. Right? How many of you are like stereos and those kind of stuff and talking in, oh, you have HTTP, but I have HDMI kind of thing? Okay. Yeah, one, right? So hopefully, you know, so this stuff will be useful. So what I'm going to do today is like kind of recap a little bit on JPEG. We kind of ended on the JPEG front, and then go on to try to look at the fundamentals of video. What are the issues for the video, right? I kind of rearranged the lectures a little bit because the lecture for Thursday said we'll look at audio, then come back to video. I don't know why I split it up, but now we'll look at video for next 3 lectures, then look at audio, then go on to the systems aspects of it. Okay. So to recap, one of the things we mentioned with JPEG was JPEG tries to optimize for what a human being can see. Human being can see a lot of details on in the luminance or in the brightness scale, not on the color scale. Color, you just need patches of color. So essentially, you split the RGB into the YCD, CR, or one of those domains, where you can split the luminance and the chroma component, and then you do some subsampling. I'll talk a little bit about that in a few slides. Essentially, you drop a lot of components of the color. So if you think of it, it's more like essentially for every 4 luminance values, you have one of the color values, right? And you actually, the 2.0 means that you average the 2 CB and CBR components. So essentially, you have very little color component. So once you have this, you transform them to the frequency domain, essentially using a discrete cosine transformation, where all the operations are integer operations. Right? You transform them, and then you drop the higher frequency components, and then you get the lower frequency components. Depending on how much you keep those, you have a tunable way of setting the how much encoding you want, and that's the lossy component. JPEG is a lossy compression. That's the lossy component. So you can drop a whole lot, or you can keep more of those. And once you do that, you do Huffman encoding, which more details you will probably see it in algorithms class. Essentially, try to build a tree of the different subsequence of bits, right? And the longer subsequence, you give the shortest bit length. So it's a variable length encoding. So that's a lossless encoding, and you store that file, and then you reverse the same operations to get the image back. So Wikipedia has lots of nice pictures. One of the image they did was take an image and then go from here on lowering the quality, right? So there's better quality here, and in steps of 10, you kind of reduce the quality. And again, I'm not sure how well you can see it on the display, but essentially, if you go to something over here, right, you see basically blocks. So JPEG operates on 8x8 blocks, and the lowest frequency you can think of is the DC component, which essentially is the average color for that square. So you can see that over here you see these little squares. Each of them has the average color for that block, right? And as you move over here, you add more frequency components, so you get more detail, right? And over here, if you look on your screen, you'll see that it's kind of sort of blocky, but you can still see some stuff. But over here, you can see a lot more of the stuff, right? So JPEG is and there are other variants that people work on. JPEG 2000, which uses wavelets and stuff. We're not going to go through the details of those. It's been good for web technologies. looking at browsers and stuff, right? So, what do you think? Do you think it's good enough for printing? Most of your cheap cameras take pictures in JPEG directly, right? So they already did this, and then they dropped some of the components, right? Except if you have high-end camera, it lets you choose in RAW format or TIFF format or what have you. Right?
But see, this is kind of a JPEG isn't one, like as you look at this image, it's all a JPEG quality, right? Mm-hmm. So saying, how is it for printing or how is it for medical imaging, it's got this quality knob that you can kind of turn depending upon what you want. Mm-hmm. And you can turn it so that it's a virtually lossless format, mm-hmm. if that's what you want.
Let's say it's going from here to here, right? Let's say you're not dropping any component here, and then you're dropping a lot more here.
And yes, the size gets bigger. But yes. I mean, so but to say, how is it for all of these different fields? To me, the answer is it can serve all of those fields mm-hmm. because of the fact that it's got this knob. I mean, if what you want to say is when you pick this quality setting, how does it serve in different fields? Mm-hmm. That's kind of a different question.
Yeah. So yes, that's the excellent point, right? So it lets you choose these quality levels, right? So you could argue that it should serve any kind of operations, right? If you look at the amount, the file, the compression ratios that you get, the good range is like sort of from 80 to 40, 50, that range, right? If you go beyond that, if you go higher, then essentially JPEG would be terrible, right? You should think of some other compression, or you get very little compression, right? And if you go below 30 or something in terms of quality, you don't get much gains, it kind of bottoms out, right? So for the printing, for the most part, it's okay because if you're talking about a consumer camera, the lens is small, the CCD is not that good and everything, so it kind of works out to be okay, right? And then you should choose like a quality factor around 70, 80, something. But they also have like little modes where it says, I don't know if you had one of those cameras, it'll say fine, super fine, or like good and low and all those things. And if you go lower and lower on the scale, you're trying to go more towards this area. And you may see some other artifacts, right? Doctors don't like JPEG. They just don't like JPEG at all, right? They just don't want to hear lossy, right? Regardless whether it means that they can see the difference or what have you. They would much rather pay the cost for lossless, right? It just bothers them that you may not be actually seeing something, right?
We do. Room 118.
Even though, so if you think about the other aspects, so what doctors really want is a very high DPI display, like sort of your film, which is actually very high amounts of data into a small chunk, right? So your film is sort of like this small, and it can be blown up to fairly large sums, right? But your display, the kind of display that you have in your screen or something, it's not that high quality. It's 600 DPI or what have you, right? So the doctors can't really see what they used to see in the X-rays or what have you. But they just don't like it. They just don't like the idea of it being lossy because they don't understand technology. They don't understand technology. They'd rather get the higher quality out of it, right? So are there any questions about JPEG? We'll use some of the JPEG in the video sense, right? So the textbook talks about some of the different ways that you connect and how these things work for the video domain. So the best analog format cable that you can, I think we talked about it in a previous classes, is the component video, right? Usually have this green, blue, and red, right? So when you think of the RGB coordinate scalar, YCBCR, so essentially you can have one cable for each component, right? So this is the best quality you can get because essentially all the color components have their own cable. So if you have one of these TVs, right, you can play around with like removing one of these things to see how the colors change. So if you just choose the white component, you'll see the luminance. It'll basically look like a black and white screen. Then you can try the CBCR just to help yourself look at this stuff, right? And these are usually on the higher end of the of DVDs or those devices. The lower end of those, slightly lower, is the S-Video, which you've probably seen in your slightly older laptops and stuff, right? So essentially, it has 4 pins, which corresponds to 2 cables. There's one for luminance and one for columinance, which includes the CB and CR. So it adds CB and CR, sends them in one cable. The luminance is in its own cable. So it's still not that bad, but the color component is mixed up. You shouldn't notice a difference because the color component, anyway, getting cropped left and right, so you shouldn't notice a difference. But as things go, these are lower quality than the component video. And then you have a single RCA, sort of the next lower level down is a single RCA cable that you probably see in a lower-end TV, right? Which essentially mixes all the lumens and columinance, everything into one cable. So you've probably seen 3 cables, 2 for audio and 1 for video. That one cable has all the 3 components. And so there's a possibility of them mixing on transmission. Even cheaper is the, your VCR has the output that you connect to the TV input. It will be channel 2, channel 3 or 4, what have you, right? Essentially here, the VCR is converting everything to broadcast signal. It's going off, and then you're taking the signal off. So that's the lowest quality video you can send. On the digital front, these are videos. So you can also have the RGB, which is like your VGA adapter, sort of like what the what this one is, right? Like when I choose this one, right? This is a VGA adapter. That's an analog, analog, sort of like the first one we saw. Different cables for different signals. On the digital front, you have the DVI, right? Digital video interface. So this laptop talks DVI, but of course, we shifted to the analog format. And essentially, it has different resolution and different links. So they talk about single link and dual link, depending on how many pins there are. So if you look at this stuff and you see the number of pins, right? So if you have one of those 30-inch or so LCD panels with this kind of resolution, you're talking dual link, right? I think Apple has one of those, the high resolution one. You can actually go up to this resolution, which is pretty good, right? So yeah, that's way bigger than your VGA 640 by 480 or something, right? So this is, you can send lots of data, right? So that's on the computer side. The computer side, we have the DVI and stuff and those kind of cables. On the consumer side, you have the HDMI, right? It used to be a little bit different pin, and I think the latest pin structure is sort of like this, right? How many of you seen this? In what? Okay, in computers. This should be more of a TV kind of output. So it should be like from your PSP.
Oh, I've seen it with DVD players and with cable boxes.
Yeah, DVD players, yeah, cable boxes, definitely, right? You probably don't need it for DVD players because the DVD is not high resolution. We'll see in the next few slides. For DVD, the other things we talked about should be fine. But if you want to send full resolution, high definition, you want something like these, right? And I think it's a fairly new thing, like within the last couple of years, right? So the nice thing about this from a consumer perspective is there's one cable, and which has audio and the video, everything going in one of these things. It's very high resolution stuff. It can do 30-bit, 36-bit, 48-bit video. None of the consumer stuff is at that rate, but it can do that, right? You can send audio uncompressed. You can also send audio in Dolby True HD and DTS HD, which are the next generation of high definition audio and stuff like that. The stuff that all the companies love is the fact that it has DRM built in, right? So what they're really afraid is with the digital transmission, essentially your player is sending all the digital signals off to the screen. So somebody could take all the digital signals and store them and pirate them or what have you, right? So they're really afraid of that. So they have this notion of a HDCP DRM module, which essentially encrypts all the bits on the wire, right? So from your DVD player to your TV, on the wire it's all encrypted and it's unencrypted on the other side, right? So the way they use that is so some of these like the HD, DVD, and Blu-ray, right? These are the next gen or the high definition DVD replacement for the ones we have, right? There's a big format war going on, but essentially both of them try to add this restriction that if you don't have one of these interfaces that can actually do HDCP, you'll be watching the video in the DVD quality, which irks me, but you know. So if you go to Best Buy or something and you see a HD DVD, how many of you seen a HD DVD player? So I think they have it up in the front, right? And it looks cool, it looks nice and everything. But unless you have one of these stuff on your TV, right? Unless you bought your TV in the last couple of years, which unfortunately I didn't, so you can't really play it in high definition, right? But if you had, then this can do a whole bunch of nice stuff. So, but there's a move to merge these two, merge the DVI with the HDMI, so that computers and the TVs will have the same interface. Right now you have different stuff. So if you buy a monitor for TV, to use that for your PC, you have to either support both or figure something out. But pretty soon we'll have one connectivity to connect your PC and your appliances, right? And then we'll have another set of restrictions on what you can do with your players and stuff. But it's interesting times. So those are the different kinds of restrictions that Chaper said technologies that are out there in terms of what they want to send, right? So going back to the analog video, which is the NTSC TV that we've been seeing for a while, right? So the TV signals there is interlaced, right? So essentially, back in the days, they couldn't really send a good level of data. So the signals are interlaced. So what you do is, if you want to send a scene, right, you kind of split them into different lines, right? And you take all you first draw all the odd lines, right? And then you draw all the even lines, right? And that's the interlaced format. So when you watch a program on TV, essentially it's drawing one half of the picture, and then the other half of the picture, then the other half of the picture, and the other half of the picture, and so on, right? It's doing it at 60 times. Essentially, it's creating new content every 30 times, right? So your eye compensates for the motion and stuff, so you essentially see a good quality picture, right? The other way of doing this is to essentially draw all the lines at once and do it 30 times, right? And that's called progressive, right? So it'll be more clear when you talk about HDTV that they support both these modes. Right? Yes.
So the book had that too, but is the slanting lines intentional?
It's the nature of the CRT, because if you go deeper into how the CRT and all works, right? There's an electron gun in the back which is sending the signals out, and then you have plates up here which are either pushing the signal or pulling the signal. So the way the currents flow and everything, it tends to be slanted. It's not as slanted as the book makes it. The book makes it look like it's very slanted, right? But it's slightly slanted. there's no artifacts of this CRT technology. We stuck with it, right? Because you're having a field here trying to draw the thing, right? And one of the things that you, so NTSC has a notion of, so when the signal comes here, right, it has to know that something is ended, it has to go back, right? And it has to start doing this, right? So there's the beam, if you may, is kind of going this way, this far, and then something is making it go back, and then going back, right? This reflector is going on. So it has to figure out when it has to go back, right? You can either do that by timing. You can figure out how long it takes for it to go this way, and then figure out how to go back and stuff, right? NTSC does it self-timing, right? So when it comes here, it knows that it's end of line. It has to go back to the next line. The way it does that, it has a notion of blacker than black, right? So if you really are tuning your TV, right? There are DVDs out there you can use to tune your TV to match the gamma of what NTSC expects your TV to have, right? So the worst possible setting for a TV is the one that it comes with by default, right? When you buy the TV, the color setting it has is the worst possible setting because it's designed for you watching the TV at the store, right? With all the lights and everything, so they kind of crank up the color and all those things. And that's the worst possible thing because it's adding all kind of stuff, right? So you can call this as it's making the picture pretty, or you can call it as distorting, right? So if you look at some of the modes, you can actually tone down everything. You can turn down a whole bunch of stuff. And one of the settings would be to set the black level, right? So all the pictures in NTSC is slightly bright, right? Because they use the notion of a blacker than black or a true black to figure out that it's end of the thing and then go back, right? So if you ever try to crank up your TV all the way through, beyond this your picture, right, you'll see the real black. Your picture will not be, it'll always have slightly higher offset, right? And it uses that to figure out when to go back. So it uses 525 scan line, which is essentially these lines, right? So half will be in one sweep, another half will be in another sweep. And it uses a 29.97 frames, and the discussion is in your book on why the difference. It needs a little bit to send data and stuff. So it's not exactly doing 30 frames per second is slightly lower, right? And so that tells you how many scan lines are there, how many lines are here, and that's set by NTSC, right? So the next notion is how many samples do you have per line, right? And that gives you the quality of whatever you're looking at. So your VHS tape does 240 samples per line, right? So if you look at it from a pixel perspective, it's essentially 240 by 525, right? Your SPHs can do 400, 200, 425. Different camcorders can do different stuff, and the mini DV can actually do quite a bit higher, right? So that tells you how much information there is that is being either captured or sent. And PAL and SECAM, which is in the rest of the world, in different parts of the world, they have higher scan lines, but they refresh slower, right? They refresh every 25 frames per second, and it's kind of tied to the frequency of the electricity that is 50 frames per second, right? And the amount of data that is sent in the NTSC is 6 megahertz, and the PAL and SECAM is 8 megahertz. So you actually send a little bit more. So PAL and SECAM by default are slightly higher definition than the NTSC signal, right? How many of you have seen PAL or SECAM? How many of you actually noticed that it's actually much nicer than the NTSC? It's actually noticeably much nicer. But the thing is, you will see a flicker a lot more. Especially if you go from here to there, you'll actually notice the flicker, right? So the flicker is what you set in your monitor. So in a computer monitor, you can set the refresh rate, right? Unless you have a really cheap monitor that somebody threw out and you kind of brought in, you don't run it at 50 or 60, right? At 50, 60, you can actually see the flicker, right? You want it at something higher than that, so it has a clear screen. But TV, you're kind of stuck with that. So the problem with all the TV and stuff is you need to have something which sends all the high amount of information from the TV station back to your home, right? So you have to use this, either the wireless or cable or what have you. So the more resolution you have, the more frames it has to send, right? You need bandwidth, right? And in the US, the 6 megahertz is the channel width that you see on your TV, so you're kind of stuck with that, right? So even if you go to HD, you're kind of stuck with, I mean, you can't change, you could change this stuff, but it's pretty disruptive, right? You could actually try to combine channels as whatever, but you can't start from scratch and then go from there. So a lot of the things you need to do, you are doing in software, you're doing in terms of compression and stuff to get as many bits as possible, right? So even if you take, like, for example, this 525 by 240, right? So if you look at 525 by 240 by 24, right? How much is that? I don't know. So if you so essentially if you do the math, it's 525 times 240, right? That's the width and height, times 24, right? That gives you the bit rate, right? And I'm not sure what that is, but it's probably maybe at this level because it's not being compressed at this point, right? You definitely can't say anything like high definition at that rate. So there comes the chroma subsampling, right? So if you want to send like all that much data, you are essentially killing your system, right? So again, go back to what we said on the JPEG stuff. So essentially what we do is we drop the components that we cannot see. So all of them, you should change them into YCVCR or all its variants. Right? So you change the signal from whatever you have into a luminance and luminance signal, and then you drop the chroma stuff, right? So you refer to 4:4:4 as you have all of Y, all of CB, and all of CR. If you say 4:2:2, you have all the Y, every other CB and CR. So you have half of what you have, right? And if you have 4:1:1, you have 1/4 of the CB and CR. And if you talk about 4:2:0, it's essentially you take the average of CB and CR and you have it twice, right? So you're doing a subsampling and then you're elongating. Essentially, it's like the 4:1:1, except the CB, you see a lot more of them averaged, right? But you can think of them both as the same, right? So NTSC uses 4:2:2, so it drops some of the chroma component. And your DV tape uses 4:1:1, so it has half the color information as your NTSC. And JPEG and MPEG and all uses the 4:2:0, which is a slightly different variant of that. And your HDV camcorder, the one which is out there, is also doing 4:2:0. So essentially, you drop a lot of color components, and so you get some compression right there. So next, the logical transition is towards high definition TV, and the first generation high definition TV was actually in Japan, and they actually had 1125 scan lines, and they could do that because they were essentially broadcasting it over satellite, and since Japan was not all that big, they could have 1 or 2 satellites reaching the whole country, so they can afford to have all that bandwidth, right? So when you had to go to the US, there's a big war. I think it started in like mid '80s and stuff. It's still ongoing, right? Again, textbook, it used like the last but one rule was we are supposed to go all digital by this year. I think they moved it back to 2009, right? So essentially, they were trying to figure out how to have HD while still having the older systems up and running, and what's the transition model and stuff. So right now, both of them are transmitting. You might have seen high definition TV. These are the broadcast quality, what's expected. So broadcast HD is MPEG-2 video, right? And we'll see when we go to the compression. This is not the state-of-the-art compression. So if you do MPEG-4, you could actually do much better, right? But the technology is only now catching up so that you can actually do the MPEG-4 level of compression. And MPEG-4 is not, so the better compression you have, the more CPU or more juice you need, and the technology has to catch up to make that possible, right? And it's a Dolby AC3 audio for the surround component. So by default, the HD has to be MPEG-2 and AC3, right? It can do surround channel 5 if it wants, but the default is AC3. So the resolution that it supports, the two high resolution it supports is 1920 by 1080, right, and 1280 by 720. So these are the two resolutions that are true high definition. It also supports lower definition variants. If you look at the table, there's a whole bunch of these things, but essentially these are the two high definition formats, right? The 1920 by 1080 is I, it's interlaced, right? So it essentially it does the interlacing stuff. Whereas the 1280 by 720 is a P, right? Which means it's progressive, which means that it doesn't do this line business. It refreshes the screen every, a new scene every 30 times, right? So in terms of the bandwidth requirement, this is slightly larger bandwidth requirement, right? Because, I mean, obviously it's a bigger screen, but you know, it has this scan lines going for it. This is a higher bandwidth requirement. This is a slightly lower requirement. Different TV stations choose different formats because of whatever reason, right? So Fox and ABC, and actually Fox is of the ESPN, they wanted the persistence. So if you're doing games and stuff, right? If you're doing something very high speed, you're supposed to notice the interlacing, right? Whereas if you're doing more of a movie or something where things are not moving that fast, this interlacing should be fine, right? So ESPN naturally chose the P format, and your ABC and CBS chose this format. This format will have a lot more detail if you don't have things moving really fast, right? So if you're having movies or some things, you may find you would tend to like this one over this one, right? So there is another format which is the 920 by 1080p, which is actually doing progressive at this rate, right? Unfortunately, you cannot broadcast that much bit rate through the channels you would have. So your Xbox 360, PSP3, and all those games would do 1920 by 1080 times in P format, right? Where it's replacing everything every so often. So getting this kind of display on the screen requires lots of bandwidth, and that's why you need the HDMI and stuff like that. So essentially, it's 1920 times 1080 times 24, right? Let's say this is 2, right? 2 and 1000, so it's 248 megabits per second or so, right? So that's a lot of bandwidth. So these guys can do that. And there's also other variants. You don't have to do the 29.7, 29.97 from NTSC days. We can also do 24. They call it cinematic because the movie theaters only refresh every 24 frames per second. Right? So if you want to have the cinematic view, then you could go with this model. Right? People actually like the cinematic view because cinemas are actually supposed to have a little bit flicker, right? And people like that for nostalgic purposes, right? You do notice it if you kind of watch it for a while on a good set, right? So that brings up the issue of what do you mean by good set, right? So these are all the stuff that the signal can put out. Most of the TVs that you can buy are still somewhat lower pixel rate, right? Your CRT TVs are 1024 by 768 or what have you. So this discussion is new if your TV is only this, right? Because you can actually send more information, but your TV cannot output the stuff. Only last year can you actually buy something like this, right? 1920 by 1080p, right? If you look at some of the newer LCD TVs and newer LCOS TVs, I'm not going to go into details. If you go to the Best Buy, you see a whole bunch of stuff. And those can actually display it at the 1920 by 1080p, right? And you also notice that that doesn't necessarily mean the picture actually looks good. It depends on a whole bunch of other stuff. And I still think that the CRT, Trinitron, Sony had this rate looks good, right? So a whole bunch of stuff. You'll definitely notice it if you have a TV which is like, say, the size of this wall, right? You would probably want it to be a 1080 by 1920 by 1080 stuff because you're going to see the pixels, right? Yes?
So what happens if you try and do that on a TV that size? It cuts off your picture? So what happens if you have 920 by 1080?
It's some samples. It's some samples.
Oh, okay.
So essentially, yeah, so if you for example, if you had like this for simplicity, right? If you have 1000 by 1000 as the broadcast one, and you have 500 by 500, right? So essentially you take 4 pixels here, average it, and then you put 1 here.
Okay.
So, and obviously this is like, the math doesn't work out that easily, so there's processing going on trying to average this stuff. So all the details that you were promised in the HD kind of goes out here. But the other point is, it also depends on, so there's one thing about pixels and there's another thing about how big the pixels are, right? So for example, like this screen is 1680 by 1080, right? So you can actually display all these dots, but they're very small, right? So if I ask somebody, do you prefer HD on this monitor or like a big monitor, right? You probably prefer the big one because you can actually see the dots, right? Think of it this way: if you take your film, your negative, scan it into 4000 dpi, which is the maximum amount of information you can get. The original is only this big, right? So if I ask you, do you prefer to look at it this small one, right? Or do you prefer to pick it like a bigger picture, right? You probably prefer the bigger one, right? Even though they have the same information. Does it make sense? So you probably don't really care if you have 20-inch TV, right? You shouldn't be talking about any of this. You should be happy that you're seeing a picture, right? If you have 110-inch TV, right? How many of you have seen a 100-inch TV? Those look awesome, right? But if you have one of those, right, on this matters, right? Because you can actually see the dots. Right? So there's also a notion of a rectangular pixel. Like for example, those HDV camcorders, they only have 1440 by, actually this is wrong. They only have 1440 by 1080, right? As what the camcorder picks up, right? And then it converts it into 1920 by 1080, right? So what it captures is 1440 by 1080, not some 68, right? And then it converts it into 1920 by 1080, right? Because essentially the height didn't change, right? Only the width changed. So essentially the pixels here are longer, like that kind of stuff, right? So they have other issues in terms of, for one thing, they have to make it affordable, right? I can't afford a 1920 by 1080 stuff, and they can't store it onto the regular tape, right? And so they have other issues to deal with. Right. So these are all the technology, these are all the stuff out there. I like to look at these stuff because if you want to look at the multimedia and stuff, you should have some appreciation of what people want to do, right? So systems people would love to get you 1920 by 1080p, right? So how many of you have actually seen the specs for PSP3? Yeah.
Well, what specs are you talking about?
Like how many outputs?
How many different types of outputs?
Yeah.
Well, I mean, it depends. They still want to be able to support the old-fashioned TVs, I believe. Although the final specs are early release since they haven't released the unit. For the 360, they've got they'll support 16:9 up to 1080p, or they'll support the old-fashioned. They actually got this funky little switch on the connector. It switches it between the good old-fashioned single yellow video cable to ICVCR, component video.
The PSP3 is supposed to have two 1920 by 1080p. Right? So when I heard that from some guy at Sony, right, it's like, okay, but I can't even buy, this is like 2 years back, right? I can't even buy a TV which can do 1920 by 1080p. Why would I want two 1920 by 1080p, right? Huh?
Just cut that out.
Yeah.
But they haven't even manufactured it yet. So who knows?
No, they can do it. No, obviously, there may not be a connector in the back. I mean, I don't know what. So he's the research guy, right? So they're building the stuff. They don't know how Sony's going to sell it, right? No, but it's there, right? It's there from day one, so it can't be taken out, kind of stuff, right?
Well, there is a reason from a gaming perspective you could want to do it. So you and your friend can have two different screens while you're playing.
Mm-hmm. But no, I can see that, right? But I'm saying most normal human beings can't afford to have 90 by full screen, right? But forget about like what we can afford, right? But they're supporting that kind of a data, right? So if you look at the amount of data flying out of the device to your screen, so 920 by 1080, you're talking about massive amounts of data, right? You're talking about massive amounts of data which have to fly at, if you're doing like say 30p, right? So every 30 seconds you're refreshing the whole screen, right? So you have to send all this stuff. So when you talk about real-time systems, right? This is real-time systems on steroids, right? If you're talking about like little, like things, like controlling your car and all those things, yeah, but your car, you rarely change the gear all that much, right? But here you're sending that much data over and over again. So if you skip, so here, there you're rendering, right? This is video I'm talking about, like your camera or something picks it up. Your PSP is actually rendering all those stuff, right? So if it forgets, if it can't render something at that rate, right? What's the point of doing all this stuff if you can't keep up with that much on the game front, right? So that's the stuff I want you to look at, right? So when you see the paper from USC, right? The one I talked about where they had all the stuff, right? So you're talking about 1020 HD, full HD screens worth of data, right? That's the interesting part. And when Clara comes in and she talks about so I think I briefly mentioned, right? They want to do dancing where they have a big monitor here and you dance to it, right? So your dance partner is in Berkeley and you're in Illinois, right? So you're dancing, right? So you want to dance and you want to feel like you are there. So all the resolutions matter, and all the stuff that you have matter. And you want to do it such that you can still feel like the other person is dancing with you, right? The demo looks awesome. I just can't look at it because it looks, you'll see, she probably showed, or you can take a look at it. It looks very choppy, I think it's in 3D. But the dance instructors actually love that stuff, right? So I wanted to get a sense that doing all this stuff requires lots of whatever you can throw at it, it can choose. How many of you started the project? I think you mentioned that the machine was crashing and stuff. I don't know what's happening. I didn't take a look at it, but you looked at it?
Yes, we're
Okay. So one of the things you'll notice is whatever machine you can throw at it, your video can chew and spit it up, right? So if you want to transcode the HTV on those machines, I think it takes like 12 hours or something. Right? It's a dual core, whatever. Right? You give a quad core, it's still not real time. Right? It's not close to real time. Right?
They figured at some point you're going to be able to do that, and they want to put that in there just in case.
And at that time, we'll kind of try to up it, right? Like make it into 1090.
Yeah.
I saw some references to UHTV or something, right? I mean, in terms of HDTV, right, this is technology that was dreamed up in late 80s, right? It's not something that we are designing right now, right? So when we finally reach the point where we can deal with the 80s technology, maybe then we can go to 21st century technology. But yeah, the point which really interests me is like you can actually buy these things for practically not that much, right? Still expensive, but not that much. Right. So let's look more at the video compression. So I'm going to give a high-level view and we can go into more details in the next lectures, right? So the idea here is, yes, video, like we want like a lot of high resolution, blah 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 kind of stuff. We know something about dropping some things to manage these things because we can't possibly send RGB at this data rates, but we know how to sample these things, and then we have to figure out how to compress them, right? Because if we don't compress them, we can't send that much data rates across the wire. So there are a number of different ways you can think of doing this, right? The one way is you can look at each frame, compress each frame independently, and then send it across, right? And you can use something like your JPEG to compress each frame. So if you think of 30 frames per second as 30 images shown within a second, right? Each frame you compress them and then send them independently. You'll get very good quality because essentially it's the same frame. I mean, it's different, unique frames. If you do a pass or something, you see the different frames, and that's essentially what motion JPEG does, right? And turns out it's not the best way to do things. I mean, yes, it gives you these nice set of images. You can do much better, right? So the way you do that is you again use other mechanisms. You use the fact that scenes rarely change. Right? Scenes rarely change where some part of the scene changes, but the rest of the scene remains the same, right? So if you notice that most of the scenes, so if you look at, suppose the camera is looking at me right now, right? I'm moving. The rest of everything else is sort of stationary, right? So if you can use that, then we can save sending lots of data at the expense of computation, right? If you do a motion JPEG, each frame is a JPEG image. I have to decrypt it, and that's it. I don't have to look any further, right? So here you have to have a reference frame, and then try to find out some frames in the future. You try to look at the differences, right? The simplest form you can do is you take one frame as a reference. The next frame you take as a difference of whatever was from the previous frame, and then you encode that part. And then you take another one, so on, right? All the compression, all the Huffman, all those like the entropy encodings, like lot of long repeating patterns, right? Remember that if you go back to your compression from Algo and Scos, right? If you have a lot of repeating patterns, they like it. So essentially, if things change, if very little changes, right? Then if you do the differencing, those bits will be black because nothing changed. So your compression would work very well. So you'll see a lot bigger, lot better compression ratios, right? And this works because typically when you use cameras, you don't usually show one frame, a new frame every frame is not new, right? If it is, then it's very annoying. It looks like a strobe light kind of thing, right? So again, if you look at medical imaging or whatever, this may not be true, but for normal stuff, it holds, right? And turns out that itself it may not be as good because the differencing tends to pick out stuff where nothing really happens. If you throw a ball or something, right? So what really happened was there's a background and there's a ball moving across, right? So this ball is kind of moving across. If you look at the differences, each like whole bunch of areas look like there's a difference because there's a ball of the previous frame, new frame, they all differ, right? So the ultimate idea is try to figure out that there are moving objects here. Try to figure out where these movements are going, right? So I figured out what the motion vector is. I figured out that there's object here and that kind of moved this way. So I figured out that this object was here, moved here. I figured out what this motion vector is, right? Which way it went, how much it went. So when I transmit this other side, I say, here's the reference frame, and the next one, this object which was in your PC moved in this direction for this much, right? That's the motion vector stuff, right? And then once you do this, you have to do some compensation because if you take the original image, move these objects in this way, there are still some leftover effects. And that residues I send it to you separately, right? And that's the basis for most of the compression, video compression algorithms we'll see in the next few lectures. Right? So essentially we know that very few things change, right? But when they change in a nice fashion. They don't change as if there's dots coming on and off, right? There's a thing where things move across the scene or whatever, which means that object which was here gets translated in a nice fashion. So if I can figure out what these translations are, and then I can send you the translations, or other than you actually compute back, you render it again. You say, I had the original image, I move the new objects to a new location, and whatever was left over, I fix it, right? And that's the higher level construct, right? If you think about it, it's a naive approach of doing this would be horrendously slow, right? Because then you have to essentially take all frames, you have to try to figure out where objects are, because there's no notion of object, right? So you try to figure out where objects are and try to figure out what is moving where, right? And at some point, if you fail, like, so if a scene changes, right? If you go from one scene to another scene, these algorithms will try to find out that there's a movement or something, and they'll find that the residue will be quite high because there's a different scene. So by accident, some things may be similar or what have you. So when that happens, they kind of back out and send the whole block itself. So to do exhaustive search is sort of like what you do on a sequence search. You take each block, try to figure out where it might have gone. So you try to see all the neighborhood where it might have gone, all the neighborhood it might have gone, all the neighborhood it might have gone, right? And try to do these predictions, right? And as you can imagine, these are extremely compute intensive, and that's one of the reasons why compression takes a long time. So you're taking a 1920 by 1080 image, right? 30 of them in a second. So each frame, you look at the frame, you try to look at the next frame and do this matching, right? And then this and the next one, you do the matching. This and the next one, the matching. This and the next one, the matching, right? You do the numbers and you're very quickly exploring this stuff, right? Ideally, you would want to do as much as possible, as much of into the future as possible, right? Which is also the most computationally intensive. So you have to balance these things, right? So there are different ways of doing this search. So one of the searches you do sequential, like I said, you look around to see where things might have happened. Logarithmic search, you scale the image down, right? And then you take the smaller image and try to see where the object is going, because it's easy to predict, because you have a lot fewer objects to work with, and then you kind of scale it back, right? So in the smaller image, I see it's moving this way, and then I know where I should look for it in the larger image. And then you can have variations, and so we'll see some of those in the following stuff. So essentially, all the stuff about MPEG and all those things use something like this, right? You cannot do motion JPEG because that doesn't give you as much compression, right? So the compression takes a lot of time because it's trying to figure out what moved and then try to figure out these motion vectors and send the stuff. The better the predictions are, the better compression you get, right? So when you're doing the project, there may be some settings, where you can say multiple pass, right? Where you'll figure out what the motion vectors are, the one pass, and then try to do it again to see if it can come up with a better pass, right? You can do 2 passes, 3 passes, and your more expensive tools like Adobe Premiere and all lets you go through as many passes as possible to find out the best motion vectors, right? And if it comes out with the best motion vector, then you get the best compression that means your hopefully your picture will look good or what have you, right? And those are extremely time consuming, and that's probably what you'll see. Does it make sense how you? It's a very high level, but you know that's what you're trying to do. And there's a lot of math trying to figure out where these vectors are going. Like, it's also very boring math, right? Which is really good because then you can implement that in hardware, right? It's not very complicated. It's not doing floating point arithmetic or something. It's trying to look to see where the motion happened and then trying to do the stuff. So essentially, you see more and more of the stuff being done in hardware, right? The more it looks, the better the space it looks. You know, the more compression you get, and the more processing you need. So that's one of the reasons when you go from MPEG, you know, as you move along, MPEG 2 and MPEG 4. MPEG 2 is what you're seeing in your TV and stuff. MPEG 4 is the Apple uses that for all its audio. And if you have, I know for a fact that Dish and Satellite, Dish and DirecTV, the satellite providers, they're moving towards MPEG 4, right? How many of you have satellite? I'm not sure what Comcast does, right? Because I don't have Comcast, I don't know what they do, but they ought to be going towards MPEG 4 because the hardware is finally catching up that they can actually do compression in hardware and decompression in hardware that they can actually send. So if you go from MPEG 2 to MPEG 4, your pictures won't look any better, right? All the compression is not about better picture, even though the marketing, they make it look like it's better picture, right? You know, like now you have MPEG 4, right? It's not about better picture because the picture, all these things actually make the original picture worse anyway, right? So it's not about the picture, it's about how little space you can send. So what is true is between MPEG 2 and MPEG 4, right? If I say I can only give you 1,000 kilobits per second, MPEG 4 will look better than MPEG 2 for the same bandwidth or storage size, right? But in absolute sense, picture quality would probably be the same, right? So some of like your TV and all are going towards different variants of MPEG 4 because MPEG 4 lets them send more data through your channel, so they can actually have more channels and stuff, right? Which necessarily does not mean that you get better quality, but you get more channels, right? And the other thing is your satellite and your cable do not have to follow this notion of high definition, right? The 1080 and all those things we talked about is for broadcast over the air specification, right? So what Comcast calls as HD has nothing to do with this, right? So Comcast can pronounce that 640 by 480 is high definition or what have you, right? So I don't know what they do, but you know that's so the definition of high definition for over the air is not the same as what it is for Dish, right? So Dish is actually lower because I know the artifacts are more, but they just do that. Okay, something else. So I forgot something about these satellites. And when they broadcast these stuff, so how many of you have seen over there high definition? So when they do the over there high definition, right? They don't have, they can subdivide it into smaller channels. Like for example, CBS here, right? Subdivides its digital into CBS 1, 2, and 3, right? 1 is CBS, 2 is UPN, I think 3 is Weather Channel or something, right? So even this, whatever bandwidth they get, they can subdivide it into this lower quality stuff, right? And that seems to be the way that these guys go, right? The only time I've seen full high definition without this partitioning is during the Olympics. Right? Our local NBC was sending all the signals and all the, just one broadcast. But typically they try to do all this little stuff. Oh yeah, the other thing which, if you watch some of these like I know we have Dish. So I know Dish, right? So Dish tries to sometimes do high definition by faking it. Essentially, they take a low definition picture, stretch it this way, and then send it in high definition something, right? If you want to know how that looks like, look right in the student center. Student centers there, right? All the TVs, right? They take a normal picture and make it into 16:9, right? The white format, right? So if you look at the TV and the student center, they take the normal 4:3 picture, they stretch it out into this high definition format. How many of you noticed it? It's annoying, but that's that, right? So if you ever look at Dish, maybe to other channels, right? TNT does that a lot. They stretch this picture like this. So it's coming to you in high definition signals, but the content itself is low definition. Does that make sense? So it won't look any better because it's just low definition kind of stretched and sent in a nice package. Right? But of course it counts as TNT HD, but that's what they want to do. So I'll look at one such encoding, H261, right? One such compression, and the MPEG-4 is H264, right? Essentially, this was used for video conferencing and stuff. So they defined what types of image that they should have, right? And some other terms are the SIF is that size, the 352 by 288, right? Those numbers are kind of hard, but they're chosen such that they're divisible by 16, right? They can figure out good blocks and stuff, right? So these are the two sizes, SIF and QSIF. So this encoding supports those two sizes, QSIF and SIF. Of those sizes, QSIF is essentially quarter SIF, right? It's 1/4 on each dimension of the SIF, right? And it's defined as a video conferencing system, so the bandwidth requirement that it has is in multiples of 64 kbps, different kinds of stuff. So it has a notion of a I frame and a P frame. I frame is an intra frame, and P frame is a predicted frame. Right? So I mentioned that there should be some which you can trust, and the other ones which are offshoots of those. So I frame is the one frame, the one stable frame, and the P frames which follow that would be predicted from the I frame. Right? It can either be predicted from the I frame or previous P frame. So you typically would have I, P, some number of P's, and then another I. Right? So the prediction is like this. Right? So this P could be predicted from this P or this P or I. Right? So you can go on like this. So the longer you go, right, the more error artifacts you can create, the more things you may have to compensate, right? And the shorter you have, then you're not getting good compression, right? If you can go for a very long, so if a scene is, so ideally this I should be for every scene change, right? And if you look at the coding perspective, they try to figure out when there's a scene change, when there's a camera shift out, what have you. So from that you figure out where the keyframes are, right? More complicated things we look at are more complicated because they can do forward and backward prediction. But these ones are the only forward predicted. Which means that if you lose this I frame, this whole block is useless, right? Because you can't do any prediction without the base. And again, so when they try to create this new P frame for a particular block, if you notice that there are way too much information than what you can send with a diff frame, it's an original frame itself.